This video is about Young modulus. We need to define these two terms, stress and strain. Then we need to relate them to the Young modulus, and we need to try to carry out some calculations involving all these quantities. So here's our first definition, stress. So stress is the force per unit cross-sectional area perpendicular to the force. So if I've got a wire and I'm applying a force of 100 newtons, to work out the stress I need to calculate this area and then do the force divided by the area. When you write in a definition, it's important that we do cross-sectional area because it's this area, not for example the surface area, okay, which sometimes people write, or sometimes they just vague and write area. So it's the cross-sectional area. My recommendation to you here is that you do a separate calculation first to find the area in square meters. What sometimes people do is try and do it all in one, and the tricky part of this is always the units and converting millimeters into meters and millimeters squared into meters squared. So the best way to do it is to do a separate calculation first. So you know the area of a circle is pi r squared. So pi times the radius, so divide the diameter by 2 to get the radius. Don't forget the 10 to the minus 3, so 0.25 times 10 to the minus 3 meters, and then square it. If you try and take any shortcuts here, there's a fair chance you'll end up going wrong. So 1.96 times 10 to the minus 7 square meters, and then to work out the stress we do the force divided by the area, so that's just 100 divided by 1.96 times 10 to the minus 7, which gives you 5.09 times 10 to the 8 newtons per meter squared. So you'll notice this is like a pressure unit, it's force per unit area. Sometimes they will give you this number in pascals. 1 pascal is just the same thing as 1 newton per meter squared. Okay, 3 examples of the sort of questions you might get. So this is a nice easy one where they're giving you the force and they've already given you the area. So we just do the calculation there, force divided by area, and we get an answer. You do tend to get quite big numbers here, okay, because this is the force per square meter, so don't be scared if you get a big number there, okay, because we're usually using wires with fairly small diameters, fairly small cross-sectional areas. Slightly trickier is where, like in the previous question, they give you the diameter, so don't forget to divide the diameter by 2 to get the radius. Do the calculation first where you turn the diameter into millimeters and then square that number, and again then just do stress is force over area, okay, and get your answer for your stress. Sometimes they like to hang a mass on, so again just the complication here is that you need to just turn the mass into a weight. So again, do the area calculation first, then work out the weight of that mass. We're using 9.8 for gravity, and then again stress is force over area to get your answer. Okay, so hopefully not too difficult a concept, but lots of possible ways to go wrong in your calculations if you're not careful. Okay, our second quantity is strain, and strain is the extension divided by the original length, okay, and key things here are it's the original length, not the final length. So if I've got a wire that's 0.500 meters long and it stretches to 0.504 meters long with an 8 Newton force on it, then the strain on that wire is the extension divided by the original length. So the extension is the final length, take away the original length, and that gives us 8 times 10 to the minus 3. You might be waiting for a unit to appear here, but if you look what we've got, this is a length divided by a length. So this is just a sort of ratio. It doesn't have any units. It's got a factor of 8 times 10 to the minus 3 longer. Okay, so now we've looked at these two things, we can put them together, and we can say the greater the stress on a wire is, so the more force we apply to each cross-sectional area, the greater the strain will be. And Young modulus only applies when one thing is proportional to the other. We'll look at that again in a minute on the next slide. But the Young modulus only applies in the part of the extension where the extension is proportional to the stress, or the strain is proportional to the stress. This is the elastic region of the graph, just like it is with a spring. So what he said is the stress divided by the strain is a constant number, and this constant number is called the Young modulus. It's the constant for a particular sort of metal. Okay, it's not a constant for all metals, okay, but you can get the Young modulus of copper or brass or steel Okay, so Young modulus is stress divided by strain. Sometimes you'll see this equation. So Young modulus has a symbol E, force divided by area, divided by change in length divided by original length. So this is our stress, force divided by area. This is our strain, change in length divided by original length. Because we're dividing by a fraction here, we can turn it over and multiply by it. So we get force times length over area times change in length. Okay, just to clarify that with the graphs, if we got a specific spring, we plotted a force extension graph. Okay, this graph, as you will have noticed, seems a bit like it's the wrong way around, but there are reasons for that we'll come to later. And if we stretch a specific metal wire, we get exactly the same graph. So the extension is still proportional to the force, same shape of graph. But if we were to plot a graph of stress against strain, then we'd get the same numbers, and it wouldn't matter what the dimensions of the wire was. So any length of wire or any diameter of wire, the graph would have the same readings on it. Okay, just a couple of examples just to check that we're okay. So if we've got a sample of copper wire 1.8 meters long with a 1 millimeter cross-sectional area, and it stretches 0.2 millimeters when a force of 12 newtons is applied to it, we can calculate the Young modulus. So we'd work out the stress, which is the force, 12 newtons, divided by the cross-sectional area, which is 1 millimeter squared, so 10 to the minus 6 meters squared. That gives us the stress. The strain is the change in length, so the extension was 0.2 millimeters, so 0.2 times 10 to the minus 3, divided by the original length, 1.8. So that gives us a strain of 1.1 times 10 to the minus 4. So to find the Young modulus, we just do the stress divided by the strain, stick that in your calculator, and you get a Young modulus of copper being about 1.1 times 10 to the 11 pascals. Okay, these are sort of typical questions you might get. So steel wire, 2 meters length, cross-sectional area 1.2 times 10 to the minus 6 square meters, 24 newton weight hung from it, stretches elastically, so we can remember we can only use these equations if the extension is elastic. Gives the stress as the force divided by the area, so 24 divided by 1.2 times 10 to the minus 6 gives us the stress. Okay, we know Young modulus is stress divided by strain, so if you rearrange that, strain is the stress divided by the Young modulus. So that gives us the stress that we had here divided by the Young modulus, which will be given to you. Of course, you haven't got to learn any of these as facts. You'll always get those in the question if you need them. So the strain is 1 times 10 to the minus 4. But remember, the strain is not the same thing as the extension. The extension, the change in length, is the strain times the original length. So 1 times 10 to the minus 4 times 2 gives us an extension of 2 times 10 to the minus 4 meters. Okay, last question. So same sort of thing with brass. What's the extension produced? So this time we've got to work out the area first. So here's your diameter. Don't forget to divide your diameter by 2. That gives you a cross-sectional area. Then you can find the stress. Then you can find the strain from doing the stress divided by the Young modulus. So the strain is 5.57 times 10 to the minus 4. And then you can find the change in length from the strain times the original length. Okay, now of course if you want to, you can go back to that E equals F L over A delta L equation and just rearrange all that in one go. That might be a little bit easier. Okay, just depends how confident you are with your algebra.